Welcome back, students. Today in this lecture we will talk about naive Bayes classifier, and this is the first part of the video. The video is divided into two parts. Okay. So first we'll understand what the naive Bayes classifier is. So the naive Bayes classifier is a probabilistic machine learning algorithm based on Bayes theorem. While the assumption is that the conditional independence of the given class label, that each class label is independent of other, they are not dependent. It is widely used for classification tasks like spam detection, sentimental analysis and medical diagnostics due to its simplicity and efficiency. Assumptions of naive Bayes. The assumptions are feature independence, the first one, that each feature is independent with another feature. The continuous features are normally distributed, and discrete features have multinomial distribution. Features are equally important and there is no missing data. So there are altogether 5 assumptions. To make the foundation, we will actually discuss all these 5 assumptions in detail. So let's say feature independence. What it does mean? Simply means the naive Bayes assumes that all features in the classification are independent of each other. So we have one feature, that is x1, it's in input, x2, and we have xn. So there is no relationship between x1 and x2 or with any other feature. Similarly, it applies for x2 and all the features in the data set, that all the features are actually individual. Okay. So what this will imply? This drastically simplifies the computations because the joint probabilities can be decomposed into the product of individual probabilities. Okay, by this simple assumption. The formula of computing the joint probability also requires certain other things which are not needed. You only need the probability of x1 when y, and you calculate the dot product, and it becomes the simple calculation. So in practice, the features are really completely independent. That is an obvious thing. But however, naive Bayes often performs well even when this assumption is violated. Okay? Although it is assuming that there are no dependence between the feature, but it works well in the real practice. Now for the continuous feature, what it is assumed is that each feature is normally distributed. Normally distributed, that it assumes that the Gaussian distribution is there. And how do you find? You've seen the bell-shaped curve. So this bell-shaped curve, this is a normal or a Gaussian distribution. Okay? It is not skewed. Okay? So that means the mean median mode all lies over here. So mu of y and rho x square are the mean and the variance of the feature of x for class y. So mu is the mean, this is the mean, and this is the variance. So this assumption enables smooth probability estimation. But if the features are distribution is skewed or multimodal, it may reduce the accuracy only. How this graph can be skewed? For example, Okay. Another way is clear. So this is left skewed and right skewed distributions. So this is not needed. We need this type of distribution of the features. Okay, that means all the values of that particular feature, okay, try to form this curve. Tries to form this curve. Okay. So this is assumption number 1. For discrete features have multinomial distribution. If the feature is discrete, it is assumed multinomial distribution within each class. For categorical or count-based features like words, counts in document, NiPies assumes multinomial distribution. Especially common in text classification. Text classification is spam detection. Okay, where the frequency of word is modeled. Okay, for efficient, and this assumption is very efficient for handling high dimensional discrete data. Okay, and the equation is factorial n by x1 factorial x2 factorial till xn factorial, then you have a pi probability of I over x starting from 1 to n. Okay, so this is a multinomial distribution assumption. Okay, now all the features are equally important. That is one of the most important features. Factors, you can say. Now let's understand that we have an x1, we have x2, we have x3, we have x4, and this is your target, let's say y. Okay. Now each of these would have certain values. Let's say I'm representing the values with the help of symbols. Okay, so that so let's assume this, and this is the your output target. Okay, so that is 4 features are given in the data set, and we assume that all features are equally important. That is, it would be difficult for eliminating any feature in this data set. Okay, so that means x1 is affecting with an equal amount the target output. x2 is also affecting with same effort and same equal amount to x2 on y, and x3 and x4 have same kind of effect. You cannot assume that under certain conditions in a data set x2 and x3 have less importance than x1 and x4. So all features are assumed to contribute equally in determining the output. Okay. So it says all features are assumed to contribute equally to the prediction of class label, that is output. NiPies does not weigh features differently. Every feature is treated as equally important in influencing the output. In the real world data, some features are more predictable than others. Yeah, you can have that. Without feature selection or weighing, the performance may suffer. That is one of the assumptions. And last is that there are no missing data. the data should not contain any missing values. The algorithm assumes that all the input features are present in every instance. Why so? Because it calculates the product of the x1, x2 probabilities for certain output y. Now if that data is missing, what you will assume? 0 or some higher value. So that if you assume 0, then entire expression will be equal to 0 because it is in multiplication of probability of x1 over y and x2 over y and so on. So that will be equal to 0. So you can't have missing values. The missing values can be distort the calculation probabilities and lead to incorrect predictions. Typically, missing data must be imputed or removed before applying the naive bias. That is, if you are using naive bias over the certain data set, then you have to actually remove the missing values or substitute the missing values in pre-processing phase only. Okay? Okay, so we'll start with the Bayes theorem. So it's a probability of x over y, where xy is given, probability of y is given divided by probability of x. So what we do, we assume posterior probabilities. Okay? The probability of class y given the feature set x, that is posterior. After that, assumption has been made. Likelihood, the probability of feature x given class y, and p of y is the prior probability, the probability of class y, okay, and p of x is the evidence or the probability feature of set x used for normalization. Now this is the first part of the lecture series. In the second part of the lecture series, we will do a problem. Then everything, what is p of y, p of x over y, you will get to know. Okay. So for that, but it is very important from the theory point of view that this is different from this. One is known as posterior, other is known as likelihood. P of y is prior, and x, p of x we call as evidence. So someday, if you are reading some text, you encounter these kinds of words instead of this expression. So you should understand what they mean. Okay? Now, so the key assumption is that all features are independent. So if the features are independent, there is no correlation, then we can simply multiply x1y with x2y and xny. Okay, so we can write it. Thus the Bayes theorem simplifies to what it simplifies to? P of y, probability of y, given all the input features, what we can do? We can have P of y multiplication of or xi given y divided by the px, that is evidence. Okay. So this assumption makes the computation efficient, but it may not always hold in real world scenarios because there is some kind of a linkage between feature 1 and feature 2. If your height is more, your likely body weight will be on the higher side because you have a high, the length of the bones is high, so obviously the mass will be high because, okay, and the mass is high, so that means weight can be high. Okay, so that is a relationship between height and weight. The lesser the height, okay, you can grow in sidewards, but normally we have a correlation between height and weight. Okay. Okay. Now types of naive bias. So first is the Gaussian naive bias. You've seen this formula earlier also. So if we have probability of xi for a y given target y, that is 2 upon 2 pi rho square by y, and this is xi multiplied by mean of y minus mean of y divided by 2 rho square of y. Rho square is the variance, okay, and mu is the mean. So this is Gaussian naive variant of naive Bayes classifier. The other types of classifier can be multinomial naive Bayes, used for text classification where feature and words are counted, or term frequency, commonly applied in spam filtering and sentimental analysis. Then we have Bernoulli's naive Bayes, BNP, used for binary feature vector such as presence or absence of certain features. Example, if a document contains the word free and or not in spam detection. Spam mail, what they offer, the free services, free product, free iPhone, something like that. So example, spam email classification using naive Bayes. So problem statement, we classify emails as spam, yes or not spam, no, based on two features. So contain free, as free is the word, and contains offer is the word, yes and no, yes and no. So you do the countings in yes and no, yes and no, yes and no, and then you apply those counted values to the formula and you calculate a probability. That's all. In the next lecture series, we'll take up a detailed example and do the calculations, so you know how to apply naive Bayes. Thank you.